welcome everyone. Today's seminar speaker is Armour from MIT. He did his bachelor studies at University of California in San Diego with a double major in physics and applied math. And then he decided to move north to the University of Washington in Seattle, where he did his master's degree in physics. And for the PhD, he stayed in the physics department, but he chose to do his dissertation in atmospheric science. His thesis was on simulation of Arctic sea ice and its variation, and simulation in GCMs and comparison to the observations. And he worked with Lou and Thompson. And since October of last year, he's a postdoctoral research fellow at MIT in Earth, atmospheric, and planetary sciences. And so Kyle has published very interesting papers on Arctic sea ice and also on the important subject of climate sensitivity and its variations that he's going to speak on today. And Kyle has written not only interesting papers, but he has written many papers in his short career. He did his PhD, he completed his PhD last year, but he has 9 refereed publications, and he has another 9 papers which he has submitted for publication. And his papers have been highlighted for excellence by Nature Climate Change and by Geophysical Research Letters. So we are very happy that he can visit us today. So let us welcome Kyle Armour.
Thanks a lot for the introduction. Turn on this mic.
Yeah. Is it on?
Do you guys hear me in the back? Is it coming through?
Back.
Not yet. Now?
Yeah.
Yes? Okay. Good. Okay. Thanks for the introduction. I don't have that many papers. My CV has more papers than I do, I think. Right, so I'll be talking today about some research that I did kind of at the end of my PhD with some people in University of Washington, Seattle. Namely, Cecilia Bitz and Gerard Rowe co-advised my thesis with Brian Thompson. Brian Rose is now in faculty at SUNY Albany, so some of the work I'm presenting is research with him. And then John Marshall, Jeffrey Scottner, and Donahoe at MIT contributed to some of the thinking on this. Most of the stuff I'm talking about today is collaboration with the first group of people, but I'll mention some kind of newer results with them as well as I go through. So just to start to kind of frame my research is mainly looking at figures like this, where you have a whole collection of climate models forced by different emission scenarios into the future. Each of these emission scenarios is a different color, but within a single emission scenario, there's a huge spread in the warming simulated by these GCMs. So the questions I want to ask are kind of what explains this spread across climate models? Can we understand why some models warm a lot more than others do in this kind of transient near-term 100-year type time scale? So the key questions that kind of motivate this is what's the role of climate sensitivity in setting the transient, global, and regional climate changes? In particular, I'm going to show evidence that there's some time variation in climate sensitivity in GCMs, and try to answer the question as to why that is. And then at the second half of the talk, pose the question: does the spatial pattern of ocean heat uptake matter for climate change? We generally think of climate change as having just the global oceans warming, but where the heat goes into the oceans makes a difference. And I want to show some evidence for that. And then kind of the general research is just what principles underlie global and regional climate predictability on kind of centennial timescales. So one way to think about the climate response to forcing is just a simple equation like this, where at the top of the atmosphere you have a global energy balance, that is the outgoing and incoming radiation, and these are anomalies from some present day states. So you apply some radiative forcing, you put CO2 in, that's R. You see some temperature response, T, and lambda T gives you some radiative anomaly associated with that temperature response. So the global climate, the global surface temperature warms, you have an outgoing long wave response associated with that warming, which cancels some of the radiative forcing you've applied. And presently we have some energy imbalance because these two terms don't add up completely. We haven't warmed up entirely to completely balance the forcing that's applied. So we have some global energy imbalance at the top of the atmosphere. And we generally drop higher order terms, order temperatures squared and higher, just because the motivation is something along the lines of these are small perturbations on top of a background temperature, which is pretty high already, 300 Kelvin. And we're talking about several degrees of temperature change on top of that. So we're going to drop that piece. So another way to think about this energy imbalance, so the global top of the atmosphere energy flux coming in right now is into the Earth, and that's changing the heat content of the whole planet. So we have C here is some kind of effective heat capacity. So dt is the heat content change of the Earth, which is equal to the top of atmosphere energy imbalance. And this is something I'm going to call, because most of the energy is just going into the oceans, we can think of this as just ocean heat uptake globally. So the top of the atmosphere imbalance, radiation coming in is just going into the oceans mostly. So you can also solve this equation. It's just a simple differential equation. If you specify C and make some basic assumptions about how C might change with time, that is, it has a pretty low effective heat capacity. As the upper oceans warm, it gets larger over time as the deeper oceans warm. But you can just build really simple models that do something like this when you double CO2. That is, you warm globally, the global average surface temperature increases pretty rapidly after you abruptly change CO2, and then it slowly increases towards some equilibrium state. And I'm going to show a lot of figures like this today, which is the way in which the top of atmosphere radiation flux evolves as a function of surface temperature. And so this is the way people usually think about feedbacks. That is, you apply some constant forcing, you apply an abrupt doubling of CO2, for instance. Initially, you start with some radiative imbalance, about 3.5 watts per meter squared in this kind of idealized setup. You just do this with GCMs, they do the same thing. But then, as you evolve toward equilibrium, you evolve along a straight line, because that line is your slope lambda. That is how the surface temperature influences the top of atmosphere radiative imbalance. And this is how we think about climate change in general, with global feedbacks. You can imagine applying a lower heat capacity, so you warm faster and evolve toward your equilibrium state more quickly. That just means you evolve along the same line more quickly. You can imagine you have less negative lambda, so I should say lambda is a negative number. That is, that when you warm at the surface, you emit radiation to space, which is canceling some positive radiative forcing. So it's a negative number, which is this negative slope by definition. So if you have a less negative lambda, you warm up to a higher temperature, starting from the same place, just evolving along a different line. If you have a more negative lambda, you evolve toward a lower temperature. And this temperature down here is your equilibrium climate sensitivity. That's the temperature you reach when you finally reach equilibrium. So each of these three slopes, you can kind of think of these as generally being these slopes as being governed by your atmospheric feedbacks, depending if you have large feedbacks in the atmosphere or smaller feedbacks in the atmosphere sets your equilibrium climate sensitivity and also the slope at which you evolve along. And then the time scale it takes to evolve along each of these lines is generally thought to be an ocean story mainly, where if you have an ocean which has a larger effective heat capacity, that is, it buries heat more deeply, then you evolve more slowly. If you have a shallow ocean, for instance, a very thin slab of ocean, if you try to warm that, you evolve very, very quickly along these lines. And so I think the general community view of this is these things, the slopes are set by the feedbacks in the atmosphere, and the evolution along these lines is generally set by the ocean. And there's this kind of clear separation. And that's going to be what I'm going to try to challenge today, to make the point that the ocean and these atmospheric feedbacks are kind of coupled in detailed ways. So what happens if you do this experiment in GCMs? So here's 16 CMIP5 coupled climate models forced with an abrupt quadrupling of CO2, because that's the experiment they did. If you just look at the global mean surface temperature change, it goes like this. There's a huge spread across the model. Some of them warm a lot more after 150 years. This is just the limit of the simulations. And then you want to ask about why some models warm more rapidly than others. So one thing you can ask is, how much does the equilibrium climate sensitivity matter for the spread across models after just 30 years? And you get an answer which is it doesn't matter that much. Basically, models with really high equilibrium warming, they're heading off to some really high value, are not that much warmer after 30 years than models with a fairly low equilibrium warming. But if you go 100 years out, there's much more of an ordering here. There's a lot more of the variance is explained. That is, the models with higher sensitivity in the equilibrium sense tend to have warmed more than the models with low equilibrium sensitivity. So somewhere between this 30-year period and this 130-year period, just the averaging theories that I've chosen, equilibrium sensitivity starts to matter more for setting the ordering of which models have warmed more than others. And so I'm going to really be talking about this kind of time scale between 30 years and 100 years of why some models have warmed more than others on this kind of very transient time scale. So just to take two of those models in detail and look at them, here's one model which these are two end members. I've chosen these specifically because they kind of illustrate this point. Here's one model which has only warmed a little bit in the first 30 years, but continues warming heading up to some really high value of temperature change. Whereas another model warmed quite a bit in the first 30 years and it seems to have stabilized, is headed off to some kind of low temperature change in equilibrium. To try to understand what sets these two models apart, we can look at this top of atmosphere energy imbalance as a function of surface temperature, space, and take a look at these feedbacks. Here's this model, CNRM, which is the one that warmed a lot initially and then kind of stabilized. It follows this very linear trajectory, which is exactly what we kind of expect from this global linear feedback theory. But the other model does something very different. It has a huge amount of curvature here. That is, initially it looks like it's headed down. If you just make a linear extrapolation, it looks like it's headed down here, and then suddenly it just curves and is headed off towards some really high value temperature. And so that's what I think really separates which models warm quickly and which ones warm slowly is the degree of curvature in the space. Models which are pretty linear are headed toward this lower value and actually equilibrate pretty quickly, whereas models which have a lot of curvature in this space look like they're warming only a small amount initially and then keep warming by a lot. And all the models basically do this. That end member, the linear one's over here and the most curved is over here, but they all basically have some curvature to them. And that's what explains a lot of this spread, is how much this curves. And so this is what I'm going to refer to as a global time variation of climate sensitivity. The idea that you don't have one set equilibrium climate sensitivity because they're all headed down to the same point where it normalized the equilibrium temperature change. The temperature change by the equilibrium, so they're all headed to this one here, and it normalized the energy imbalance by the radiative forcing in each model, so they all started up here. But in order to go from this point to this point, they all follow different trajectories, and those models which curve the most tend to be the ones that warm the least initially and warm the most later.
If you look out 100 years, do they start to converge then? Is that the message?
Here?
Yeah.
They don't necessarily, in this space they do.
Yeah.
They're all headed toward one in equilibrium. But we only have 150 years, so I'm extrapolating these to try to estimate what that
I
is.
would change
Right, so instead of the equation we had before, which, sorry, it's a little lower to see in the back, but instead of the linear global feedback equation we saw before with a constant lambda, now we're going to have some effective lambda with some time dependence to it. So this basic property of models has been noted for a long time. I think the initial papers that saw this in 1995, Murphy had a paper on this, Senior and Mitchell in 2000. What they attributed this to is nonlinear cloud feedbacks. Their suggestion is the global cloud feedback has some time dependence. That it isn't strictly a linear feedback like you like to think it is. It causes this curvature. More recently, Mike Winton and collaborators proposed that it has something to do with ocean heat uptake instead, where the pattern of ocean heat uptake makes a difference for this curvature. Specifically, they say high latitude heat uptake causes one behavior and low latitude heat uptake causes another. And this is something we'll test later. So their solution, the Winton solution, is instead of a time-varying lambda, they say we're going to have a fixed lambda, we're going to attach some time-varying parameter and efficacy to the heat uptake. And so this can account for the nonlinear relationship between H and T just because you've had some nonlinear behavior just specified. What I'm going to show is a different solution to this, which is work with Cecilia Bitz and Gerard Rowe, which is we're going to say, instead of linearizing all the global feedbacks about global temperature, we're going to linearize them about local temperature. And we're going to guess that they are constant functions of local temperature, that these things don't have any time dependence locally. But the basic idea is that you have a spatial structure of those feedbacks. And when you warm in one region versus the other, you activate those feedbacks on different time scales. And so locally they can be constant time, but globally, because you have a time variation in the pattern of warming, you can activate these things very differently. And so the basic conclusion is that the spatial pattern of warming evolves over time, and that this activates feedbacks in different regions, which causes a time variation in the global feedback. So the model we're going to show this in is CCSM4. This is just the same map of the time variation of the feedback, this curvature over time. And this is what we're going to try to explain with this theory. Just to show a little math here, you can think of that linear global energy imbalance equation as a function of local R. So here's a local energy imbalance, here's a local radiative forcing, local top of atmosphere radiative response, and some horizontal energy convergence and divergence in the atmosphere and oceans. And all these things, remember, are now local properties, but notice there's no time dependence in lambda. We're going to assume that's some kind of constant function of local properties. If you take a global mean of this, you lose this energy convergence and divergence because that's just moving heat around within the climate system. And then you can compare that to the same equation we had before, which is this global effective time variation of feedback. Just comparing these two equations, then you get a solution for the global effective feedback in terms of the local feedbacks and the time variation of the surface temperature pattern. That is, time dependence arises in the global feedback because the pattern of surface temperature changes, which is acting on all these little local feedbacks that are constant in time. And it also tells you why the slope dHdt, so d top of atmosphere, d global temperature changes with time. It's because the regions, it's the time rate of change in regions acting on local feedbacks, which is going to set those slopes. So just to see how this works in a really simple setup, here is a simple extension of that 1D model I showed earlier, just to 3 regions. Each of these regions has a different feedback, so that you have a high feedback region, a low feedback region, and a land region. So I'm calling this land because I'm going to show in a second that's kind of the separation to land, low latitudes, and high latitudes. So what happens if you double CO2? You warm up quickly in land, so that's this black line. You basically are almost near your equilibrium warming after just a little bit of time. That is, you warmed up a lot, but you haven't warmed up in your high latitudes much at all. After another period of time, the land basically reaches its equilibrium. And this green here is just the average of each of these dots where you are in space. So initially it follows the land basically reaches its equilibrium, and then it's now following this low latitude slope. And it does so until the low latitudes reach their equilibrium, and then basically follows the high latitude slope. And so ultimately, here's the land that's warmed up quickly. It doesn't warm much beyond its equilibrium temperature. Here's this low latitudes. It warms up fairly quickly to some low temperature. And here's the high latitudes, which take a long time to warm up, but they keep warming for long periods of time to a very high temperature. And so this curvature in this, basically explaining the time variation of feedback, is just which region is warming at what time, and the average globally of all of those. So this is just a very simple model, but you can see if you try to do this within the GCM, you get basically the same answer. So the way we've done this is we've calculated the feedbacks, the local feedback with radiated kernels, based on Karen Schell's approach, Brian Soden, and Isaac Helms, same approach they've used with radiated kernels. And the basic idea there is you have a kernel, here's your feedback, it's built from kernels, which is d radiation, d some field. So for instance, sea ice is a simple one. D top of atmosphere radiation, d sea ice concentration, d concentration of sea ice, d local surface temperature. And we've normalized these to local temperature. These are usually done with global temperature in this term, but because we want to get at the local function, we just normalize with respect to local temperatures alone. And this is the pattern you get when you do this with all the feedbacks in the climate system and put them all together. You end up with just a simple pattern, which is basically negative everywhere in low to mid latitudes and positive or near zero in high latitudes. So how do we understand that pattern? You can break that feedback into all the individual components. The simplest thing that's giving you that big spatial pattern is just the Planck feedback. It's negative everywhere, which means as you warm, you emit more space. But it's most negative in the tropics, at least negative at high latitudes. And that's, I think, just a simple function of sigma to the fourth. There's some nonlinearity there, where colder regions have less of a Planck feedback than warmer regions. So it's more negative in the tropics. Albedo is super simple. It's just changes in the surface reflectivity causing more. So as you start to warm up over sea ice and snow regions, you absorb more sunlight. Lapse rate has big negative feedback in the tropics, where you have a negative lapse rate feedback, so you warm more aloft than you do at the surface, which is leading to a negative feedback, more radiation to space as a function of surface temperature. And then it's positive at high latitudes, where you actually have inversions, where you warm more at the surface than you do aloft, and so it's going to give you a positive feedback. Water vapor is positive everywhere, but most positive in the tropics, which cancels a large portion of the lapse rate and the Planck feedback. And then the clouds are down here. They're kind of a mess in this model. There's a large amount of spatial structure, but there's no very clear meridional structure. So what you end up with is just this net feedback, which is negative in the tropics and positive in the high latitudes, and generally also more positive over land than it is in the oceans at similar latitudes. And so the argument I'm going to make is the spatial pattern of warming that happens activating these feedbacks. Namely, warming over the land first, warming over the tropical ocean second, and warming over the high latitude oceans third is what's causing this global time variation of feedback. So just to show this within CCSM, here's the warming that occurs within the first 10 years of doubling of CO2. It's land and sea ice as the kind of big signals. It's just kind of low heat capacity components of the system that warm up the fastest. Looking at the warming that occurs over the next several decades, you start to engage the ocean now. The ocean starts to play a role in setting patterns of temperature change. Namely, in the North Atlantic, you slow down in AMOC, you have cooling locally. There's some local cooling in the Southern Ocean. And there's also some kind of enhanced warming in the tropics. But the land doesn't stand out now as warming faster than the rest of the oceans. It's more of a kind of a global pattern, but more complicated. And then finally, on several hundred-year timescales, the simulation went out to 300 years. You need to warm, over those timescales, you warm up basically with a polar amplified pattern of warming. That's the timescale in which polar amplification really starts to emerge. And I should say, this is the limit of our run, but we, if you were going to run this to equilibrium, this would have to warm up quite a bit more, I think. So these three separate timescales, the land warming, kind of low latitude oceans, and then the high latitude oceans and sea ice, are activating those feedbacks in different regions. And what you end up with, if you just use this simple equation, the local feedbacks and the patterns of temperature change, is a prediction for how this curvature should occur. That matches pretty well with what the model actually gives. So it gets the curvature, gets the kink in the right spot. It basically is going down to the same equilibrium temperature. It has all the right time dependence. The one thing we're kind of missing is this first couple decades. It looks like we're missing some of this sort. And I don't know entirely why that is, but I think it has to do with these nonlinearities and cloud feedbacks that other studies have attributed all of this curvature to. Note that most of our answer is just coming from this Planck feedback having the big spatial dependence, right? Low latitudes versus high latitudes. A large amount of it is lapse rate. Basically anything that has a big meridional structure, whereas clouds basically don't have much of a meridional structure in this model. They're kind of very noisy spatially. It may be that the clouds actually have local nonlinearities that we're not capturing, but it doesn't look like the constant cloud feedbacks that we've assumed are playing a big role in that kind of.
So what's the cloud of points or?
Sorry, it's just the annual mean values. I'm just taking 10 running means through. Okay, so what we've shown is the atmospheric feedbacks really have a large spatial structure to them, and that means that the whole global climate sensitivity has some inherent time dependence as we warm in different regions. This has kind of large implications for how we think about climate sensitivity, because it means there's no single equilibrium sensitivity that applies to transient climate change. It really is a transient thing itself. It seems to increase over time as we go forward, as we start to warm in regions which currently aren't warming. For instance, the Southern Ocean is cooling in the observations, but we can expect it to warm at some point, in which case we'll start to lose sea ice there, we'll absorb more sunlight and increase global temperature changes at a faster rate than expected if you assume the same sensitivity throughout. So predicting climate change across models really depends on how the structure feedback exists in observations. It also depends on the spatial pattern of warming that will occur in observations. And so this also has a pretty big implication for long-term climate change. That is, what's our climate commitment? If we eventually do fix or reduce CO2 emissions, we have to come in equilibrium with the present day or close to present day values of concentrations in the atmosphere. Do we expect only a little bit more warming, or do we expect a lot more warming as the equilibrium or as the transient sensitivity itself increases over time? And so we saw a wide range of model answers to this. I focused just on one model to answer what the mechanism was, but different GCMs give you different answers to these questions. So it means that the rate and structure of decadal and longer surface temperature warming is is really an ocean story, right? We saw the land warmed up very quickly, and then after that, it's basically locked in by what the ocean does. And so the patterns of warming we see in nature and in observations are really set by the oceans. And so the oceans really play a very fundamental role in climate change beyond just global heat sinks. They're not just delaying surface warming by taking up the heat. They're also moving heat around to different regions which have different atmospheric feedbacks, and that's going to play a role in global climate sensitivity. So you can't really think of oceans as just a simple heat sink. It means that global warming really depends on the spatial structure of heat uptake. That is, if your heat uptake is occurring at high latitudes and you're cooling high latitudes versus low latitudes, that can play a pretty big role in terms of changing the radiative feedbacks globally because you're activating feedbacks in different regions. And so this last part is going to focus on the rest of the talk, which is some idealized calculations done with Brian Rose to take a look at when you force spatial patterns of heat uptake, how that changes your feedbacks globally and locally. But first, I just want to show that the patterns we saw in CCSM4 aren't anomalous in terms of the CMIP archive. So here's 16 different CMIP5 models just averaged together. If you quadruple CO2, on the left is the surface temperature change, and on the right is the surface heat flux anomaly going into the oceans. It's just a blue is into the ocean, and red is out of the ocean here. So after just 5 years, in the first decade after you double CO2, you basically warmed uniformly, but not so much around Antarctica. But you have a pretty uniform pattern of heat flux into the ocean. And if you take a zone of mean of that heat flux, you end up with this figure, which is basically negative, means into the ocean everywhere with a slight increase of heat into the ocean, in the Southern Ocean, where you haven't warmed much at all. If you wait 100 years later, you basically have the same patterns we saw in CCSM4, that is, the North Atlantic has not warmed much, the Southern Ocean has not warmed much, the tropics have warmed a bit more, or have passed that low latitude warming period. And if you look at the surface heat flux anomalies, it basically maps onto this spatial temperature pattern. That is, the regions which have warmed the most show up as red here, that's heat coming out of the oceans. The regions which have warmed the least has heat going into the oceans. So what that means is it's not, this pattern of surface heat flux into the oceans isn't driven by the forcing of the ocean itself. It's really driven by ocean dynamics. That is, the ocean is taking energy that's coming in here and distributing it into regions where energy is coming back out of the ocean in the anomalous sense. So to kind of further prove that point, another branch of work I've done with John Marshall is looking at an ocean-only calculation with the MIT GCM. That is, it's just the ocean, but no atmosphere above, but we're just forcing it with a uniform forcing and 4 watts per meter squared everywhere with some uniform feedback. And the patterns you get out of that look a lot like the couple models. That is to say, most of these patterns seem like they can be represented by the ocean circulation alone without any atmospheric heat transport or radiative feedbacks or spatial patterns of forcing. It doesn't capture everything, in particular the tropics aren't well represented where wind changes matter quite a bit. But this is no wind, no salinity, just a constant heating of the surface gets you most of these patterns. Sorry, I'm not going to go into more detail on this, but what it means is these patterns that are set by the ocean circulation are really driving the heat uptake from the atmosphere. So just to kind of go into more detail what sets the heat uptake in the spatial pattern. If 100 years after you've doubled or quadrupled CO2 in this case, the surface long wave flux going into the ocean is pretty uniform. That is to say, it's mostly just set by the fact that you have more CO2 in the atmosphere, so you have more radiation onto the ocean surface, but also it has something to do with the temperature of the ocean. So the regions which are slightly warmer have more outgoing long wave radiation, so they're absorbing less. But in general, there's not a huge amount of spatial structure here. The surface shortwave flux also has only a little bit of spatial structure. You can kind of see, for instance, a shift of the storm tracks. A poleward shift means that you have, in this case, less radiation going into the surface where the clouds have moved to, and a little bit more on the equator flank where the clouds used to be. But in general, these patterns of surface heat flux aren't really well explained by the clouds. The sensible heat flux starts to capture some of these patterns, and that's expected. That is to say, the regions which are warm are losing heat, the regions which are anomalously cool or delayed are gaining the heat, and that kind of shows up in the surface sensible heat flux. But the main thing is the latent heat flux. That's mainly, and that's just changing evaporation as a function of surface temperature, and winds also play a role. But generally, this pattern of surface sensible latent heat flux looks a lot like the pattern of the surface temperature change. And that's basically giving you the entire pattern of ocean heat uptake. So just to kind of summarize this point, it's just that the pattern of ocean heat uptake is set by the ocean, right? Because you're heating regions which are the coolest and losing heat in regions which are the warmest. So that implies an ocean heat transport that's really setting this pattern. And the next question I want to ask is, how do these patterns of surface heat flux influence atmospheric feedbacks? This is really the role of the oceans to set these patterns, but how does it influence the radiation in the atmosphere? And finally, just to take a zonal mean of this picture, you end up with 100 years after you've quadrupled CO2, you basically are close to equilibrium in the tropics, and you have these large bowls of heat uptake at high latitudes, which is slightly different than the initial case where you had kind of uniform heat uptake everywhere. So this is work we've done with Brian Rose. We're kind of thinking about this from a really idealized scenario. So we're using it in our slab ocean simulations with an aquaplanet atmosphere. And that's to say there's no land anywhere, it's just a water world of 10 meters of slab. And it's set up with a perpetual equinox, that is to say there's no seasonality to this. There's no sea ice, so it can go below freezing, but we don't have any sea ice, so we don't have any sea ice albedo feedback, and I'm messing up the story. And there's also no ocean heat transport, so this is just zero Q flux in these slab oceans. And we've done this within 3 different atmospheres, actually more, but I'm just going to show results from 3. So CAM4, CAM3, and GFDL's AM2. And what we do is we just prescribe different patterns of ocean heat uptake that are broadly mimicking what we saw in the couple models. That is to say, we either confine the heat uptake to high latitudes in red or low latitudes in blue. And we choose a value globally to amount to about 2 watts, or exactly 2 watts per meter squared of ocean heat uptake, which is about twice what the currently observed ocean heat uptake is, maybe 4 times. It's somewhere around a watt per meter squared globally. But note that it's about half of what a doubling of CO2 forcing would give you. So the top of the atmosphere forcing from CO2 is about 4 watts per meter squared. We're specifying a heat uptake in different regions of a global amount of 2 watts per meter squared. And we're just going to apply this to the atmosphere, basically. We have a slab, we're just removing heat in different regions, we're just going to ask what happens. And these shapes are kind of inspired by these SoMAS heat uptake maps I showed earlier, where in the initial 5 years, initially after doubling or quadrupling CO2, the heat uptake is almost uniform with a little bit more in the Southern Ocean. But you can think of that as kind of a linear combination of this red and blue curves. Right? You have heat uptake in the tropics and you have heat uptake in high latitudes. But after 100 years, or actually very quickly, after a few decades, you basically have reached equilibrium in the tropics. You're no longer taking up heat, but you still have heat uptake happening in the high latitudes because those regions are colder and therefore absorbing a lot of the heat. And so you can kind of think about these patterns we've chosen as a kind of fast 5-year time scale heat uptake versus a long-term slow adjustment of climate type of heat uptake. And so this is the same plot reproduced above and below, but this is just the CO2. If you double CO2 in CAM4, what the surface temperature anomaly is everywhere in the slab ocean. It's globally about 1.7 degrees of temperature change, and the pattern looks like it's least in the tropics with a little bit of polar amplification. And because it's a slab ocean, we expect, in an aquaplanet, we expect to see exactly the same temperature change in both hemispheres. This is close. This is just down to the fact that we've done like 20-year averages, and so there's some there's just some noise in the system, but it's pretty close. It's polar amplification, even without sea ice, and a global mean temperature change of about 1.7 degrees. So if we do, if we apply heat uptake at the same time that we change CO2, we end up with a very different pattern. So here's, in these black, is the high latitude heat uptake and the low latitude heat uptake. And the red here is the result you get when you double CO2 and apply the heat uptake. And so, really interestingly, if you take heat out of the surface of the oceans at high latitudes while you double CO2, remember we remove 2 watts per meter squared globally of heat, but we apply a 4 watt per meter squared forcing, we end up with no temperature change globally. So 2 watts per meter squared of ocean heat uptake is enough to cancel all of the CO2 if you put it in the right spot, which is high latitudes. But you've overcooled the high latitudes. You basically haven't changed the tropics by much. You've warmed a little bit, but you've cooled the high latitudes by quite a bit. You cancel all the polar amplification coming from the CO2. If you do the same thing but with the low latitude heat uptake, you get a different pattern. You basically don't change the temperature. You don't reduce the temperature by that much, only by about 0.4 degrees. You can also do an experiment where instead of doing CO2 and heat uptake together, you just do heat uptake individually, which looks a lot like the pattern of heat uptake plus CO2. That is, you cool the poles a lot more, but you also cool the tropics. And that has to do with heat transport. You cool the poles, and so you have more heat transport out of the tropics, which actually ends up cooling the surface temperature in the tropics. And then, in this case, you remove heat from the low latitudes, and you basically have a very uniform cooling everywhere. And then you also can probably see with I, but you can see here that this pattern looks a lot like the linear sum of heat uptake and CO2 individually. And just to check that, this dashed line is the linear sum of heat uptake and CO2 individually mapped on top of the CO2 plus heat uptake simulation. We've done both points. So I think this is pretty powerful. What this really means is the region of heat uptake makes a big difference to the global mean sensitivity to CO2. That's, I think, consistent with the ideas I talked about earlier, because the pattern of heat uptake influences the pattern of surface temperature change, which itself is influencing the radiator feedbacks in the atmosphere. And it also means that you can think of heat uptake and CO2 as almost linearly separable problems, because they add up so linearly. And this is just in the surface temperature response. They also add up really linearly if you look at the top of the atmospheric fluxes, if you look at the surface heat fluxes also. So these are really separate problems. And so what I'm going to do is really focus on just this heat uptake case compared to CO2 and ignore this one, because this can be thought of as just kind of linear sums of the others. And just to show this is a pretty consistent response across models, here's CAM4 compared to CAM3 and GFDL's AM2. All of these models have very different cloud parameterizations. They're all aquaplanets, but beyond that, they have very different atmospheres. And they all do basically the same thing. That is, they have polar amplification in the CO2 case. They have cooling in the poles when you apply heat uptake there, and they basically don't have much of a response when you pull heat out of the tropics. So something in the atmosphere is changing fundamentally when you pull heat out at high latitudes versus low latitudes. And I argued earlier that that had a lot to do with the structure of the plane feedback and the structure of feedbacks. And I think that's true in these models as well. To just take a look at the global mean feedback, you can compare, this is just for CAM4. In the CO2 case, you have feedback of about -2 watts per meter squared per Kelvin, and that's why you end up with a couple degree temperature change with a 4 watt per meter squared forcing. And in the low latitude, or the high latitude heat uptake case, you have a much reduced feedback that's consistent with activating feedbacks that are less negative in the high latitudes. And then if you have heat uptake in the low latitudes, you have a big negative feedback that's consistent with activating local feedbacks, which are very negative in the tropics. And just to see the breakdown of all these feedbacks, which ones are doing the heavy lifting, the first thing to look at is just this long wave clear sky. I've argued that's just like the plane feedback at work plus some lapse rate. That's what I focused on earlier, and that does make a difference. It was -2, it got a little bit less negative in the high latitude case, and a little more negative in the low latitude case. Long wave cloud feedbacks are changing a little bit, but the thing that's doing the heavy lifting in this particular setup is the shortwave clouds, which is this black bar. It basically has a 0 shortwave cloud feedback in the CO2 case, became a positive shortwave cloud feedback in the high latitude case, and became a very negative shortwave cloud feedback in the low latitude case. Just to show the spatial structure now of these cloud feedbacks, in the CO2 case, here's this kind of bumpy structure. There isn't a lot of meridional structure to it, but it has pretty significant spatial structure to it. And this is quantified. How we've done this in this particular setup is we've run a long slab simulation to try to back out these CO2 feedbacks. We're not using kernels here. So we did have a 200-meter deep slab, and we apply a quadrupling or a doubling of CO2, and we're using regression methods to try to back out what the shortwave cloud feedback is based on how it changes with surface temperature locally. And you can ask the same question about what the spatial structure of the cloud feedback is in the high latitude case. And in that case, it's very similar. It's slightly different in the tropics, and I'm not sure how much of this is actually
Is this all with aquaplanets?
These are all aquaplanets, yeah. So what you end up with is basically a very similar spatial structure in the high latitude heat uptake case. That is to say, the shortwave cloud radiative feedbacks aren't changing themselves when you apply heat uptake in different regions. All you're doing is activating them by temperature change in this region or the tropics. But in this case, it looks like the radiation is still behaving the same way. But we can finally compare that to a low latitude heat uptake case where the cloud feedbacks themselves are actually fundamentally changed. And so this is not consistent with what I was saying in the CCSM4 first half of the talk, where we were assuming the same cloud feedbacks everywhere. There were constant local functions of surface temperature. This is showing that if you have a large amount of heat uptake in the low latitudes, you actually fundamentally change the feedback associated with the clouds. That is to say, you can't think of them as constant local functions of temperature because they do depend to some extent on the heat uptake itself. And so I think this is consistent with what we saw, where the original figure showing the fit of the regional feedback prediction to the global mean feedback in the model was pretty good everywhere except for the first couple of decades, where it seemed to fail because we're making some assumptions about constant feedbacks. I think this may be the reason it's failing, is because we're not calculating when we have heat uptake in the tropics within that first decade. The cloud feedbacks themselves are changing with time, but we're not including that amount. But I think this is less of a problem for kind of long-term time-dependent sensitivity, because in the long term, it's mainly a high latitude heat uptake story. Currently, we have heat going into the high latitude polar oceans, and that's going to stop as they slowly equilibrate. So in that case, the cloud feedbacks themselves don't change fundamentally when you lose that high latitude heat uptake. And in a final figure, you can think of these feedbacks in terms of the cloud properties. So this is just the change in cloud water as just a rough metric for the amount of cloud, low cloud or high cloud in each of these cases. So on the left is the CO2 case, blue meaning a reduction in cloud with a warming surface temperature. So I normalize these by the local surface temperature change. So in the CO2 case, you basically get a polar shift of your storm tracks. So you get a reduction in low clouds here, increase in low clouds on the poleward flank of the storm tracks. The cool thing is, in the high latitude heat uptake case, you get basically the same pattern. That's explaining why these radiated feedbacks look so similar in those two cases. You basically just get a poleward shift of the storm tracks. But you get something very fundamentally different in the low latitude heat uptake case. That is, when you cool at the surface, or normalized by surface temperature. So cooling at the surface causes a decrease in low cloud. So this is, for 1 degree warm, you get an increase in low cloud. If you cool at the surface, you get a decrease in low cloud, which allows more sunlight in, which is trying to stabilize and warm the surface. And that's why these are really big negative feedbacks in the tropics. So something very fundamentally different is happening. If you pull heat out at the low latitudes, you basically are causing very negative, stable cloud feedbacks, versus the high latitudes, which look like you're basically activating the same exact feedbacks as you had in the CO2 case. And so this is ongoing work. We're not totally sure why this happens yet, but it seems pretty consistent across all the different atmosphere models we've shown. But as a kind of a first guess at this, I think it has a lot to do with the fact that when you are imposing this heat uptake, what you're really doing is changing the surface evaporation budget. That is, most of the heat uptake in high latitudes and low latitudes gets accomplished with latent heat flux. I showed that earlier in the CMIP5 models, but basically it shows up here in these cloud models as well, where in the low latitude heat up case, you basically are reducing evaporation that was causing this anomalous heat uptake. Same thing in the high latitudes. But you're doing it a lot more in the low latitudes. You have these larger values, and it's everywhere within the low latitudes. So that's one thing that's possibly the amount of surface moisture availability to form clouds is really being hammered by this low latitude heat uptake. But also you're in a very different regime of cloud formation. You're in this very convective regime as opposed to this mid-latitudes where you're in your storm tracks. And so I think that might be a big part of the answer for why this seems to cause local cloud changes in terms of the feedback. It's just because you're reducing the amount of moisture available to form low clouds in the tropics, but you're not really changing much in high latitudes. But anyway, this isn't really an answer yet. This is kind of just the first guess at what this is. And then note also in the CO2 case, it's fundamentally different, where you're basically evaporating more everywhere because you're warmer everywhere. So to summarize these kind of two parts, the first part we saw the global radiative feedback, that is climate stability, is really regulated by the respective spatial patterns of feedbacks. And it really matters where you warm and at what time you warm. In the second part, we saw that you can't think of the ocean as just a global ocean heat sink. You can't think of global ocean heat content changes as not mattering where it came into the ocean, because the spatial pattern of where the heat comes into the ocean really influences the radiation budget through the activation of feedbacks in different regions. And for high latitude heat uptake, those feedbacks look like they remain fairly stable. That is, that they look a lot like the CO2 activated feedbacks, but at low latitudes they really do change fundamentally when you pull heat out of the surface ocean. And what this really means is that the atmospheric, the global feedback is really set by the oceans. That is, where the oceans are moving heat to and from really changes the surface temperature pattern, which is activating feedbacks in different ways. And so climate change can't be thought of as atmosphere separate from the ocean. It needs to be thought of as the role of the ocean in moving heat from regions of high feedback to low feedback, or vice versa. And so it really means it's a coupled system that can't be separated with this linear 1D model that people generally think about. And work I'm doing with John Marshall is kind of focused on the role of the ocean in terms of this ocean-only calculation, which I haven't shown today, but give an entirely separate talk on, which is basically the ocean itself looks like it's mostly responsible for the patterns of surface temperature change in the ocean. The atmosphere is kind of secondary to that. That's it. Thanks. So we'll have lots of time for questions. I figured there's going to be something.
So let's see if there's a question. Yeah, Maran?
Yeah, I think you have to be a little bit careful about this abrupt CO2 experiments, because that's your non-linearity that you see. It basically comes from first few years of this abrupt change, but in reality there is no abrupt change in CO2. There is very gradual increase. I was wondering how this here would change if you do kind of. Have you looked at those experiments by this CFME 5, but using this one of the scenarios for CO2?
Can you repeat the question?
Yeah, the question was, what role does this abrupt 4 times CO2 forcing play in these time events? Is it still there if you look at the 1% per year simulations, for instance? The answer is it's still there. It's the reason I've chosen to go with the abrupt 4 watt per meter, or 4 times CO2 simulations, is because it really nicely separates the land, the low latitude, and the high latitude timescales, so you can see the mechanisms of how this changes. But I think it isn't just a first couple of year response that causes its nonlinearity. It's not at all related to, for instance, a rapid adjustment in the atmosphere, which happens on weeks or months. Right? It actually has to do with the fairly slow adjustment of the sea surface temperature, which happens on decades. And so that curvature isn't just the first few years; it's actually the first few decades, which has the most amount of curvature. And then it tends to lock into a pretty linear regime over the next several hundred years, because then you're in this polar amplified pattern which persists equilibrium. And so I think it really is a surface temperature mediated thing, as opposed to a rapid adjustment of the atmosphere response. But you see the same things in the 1% per year or the historical simulations if you try to estimate the forcings in those. So the 1% per year I've done, I haven't shown them here, but you get the same kind of curvature if you look at those.
Yes, great.
Are you quite get why the Elijah uptake was not tested against the uptake of Elijah? Tested high latitude and low latitude, but not Elijah. So yes, Elijah.
Why did you speak about mid latitudes?
Right.
As opposed to
low latitudes and high latitudes?
You mean in this kind of picture here?
Yeah.
Yes, right.
I guess I meant more low versus high. And
Well, I just did not quite get why you did not use the Elijah as a case to
to test for the heat uptake. You mean?
Right.
Right. We want to do something very simple, which is just high versus low that were separated. You could imagine doing this everywhere and trying to assess the role of heat uptake in every single location. I don't think we had a good reason for doing. So this is 30 to 30. So that's kind of covering some of the mid latitudes, I guess.
Right.
And this is doing 35 in polar, so it's covering the mid-latitudes to high latitudes. You're right that maybe we can separate this into more finely binned heat uptakes to try to understand it better, and that might make a difference to these cloud regimes, for instance. This is just kind of our first attempt at mimicking the patterns that we saw in the GCMs, which seemed like they were kind of high latitude, that is 60 degrees south and north, and low latitude, meaning within the tropics. These seem to capture most of that variability within the GCMs.
So does the signal reach the high latitudes after many hundreds of years because of the deep ocean circulation?
In terms of the surface temperature changes?
Or yeah.
Yeah, I think it does. I don't know. We don't have model simulations that run out that far to know.
No, so like 300 years. After 300 years, you see the warming at high latitudes, like so obviously it's because of the deep ocean circulation.
Yeah, it's right. So I think it's just you slowly start to warm because you're bringing. So the model we have for why you have delayed warming in the southern ocean in particular is because you have upwelling of water that hasn't been influenced by climate change at all. You haven't warmed that water, but then after a very long amount of time, that water slowly starts to warm because it's coming in through the North Atlantic and flowing, and it's also being warmed locally. So you will start to see a slow warming as you start to warm the ocean.
So dumping.
I think you mentioned this high latitude ocean heat uptake. Latent heat flux is the most important one, and you seem to suggest that it's mostly due to change in water vapor. That seems to be counter our intuition, but we think wind stress, wind is more important. Maybe it may not just you.
No, what I meant is that the latent heat fluxes, they're consistent with local water vapor changes in the lower atmosphere, but they're driven by the temperature and the wind. There's some temperature dependence to the difference.
So why don't you think it's a change of wind?
Oh, I think
the wind pattern, because it's changed that, right?
It certainly is affected by the change in the surface winds, for sure. But it looks a lot like the temperature pattern itself. That is, the latent heat flux pattern looks like the surface temperature pattern to first order. And the winds are, I think, playing a secondary role on this very large global scale. Locally, I'm sure they're playing a large role in setting the time scale patterns.
But wind itself probably also look like local SST too. The change of winds. That's what I'm trying to, you see what I'm trying to say?
Yeah.
There was the ocean heat content change looked like SST, that's not too surprising.
Right.
But the wind patterns change, they also look like SST, which is also not too surprising. That's really what I'm trying to say.
No, I agree with that. So surface wind shifts will change the sea surface temperatures and change evaporation. I think the only evidence I have against the role of the winds is the fact that we do this ocean-only calculation, which again I didn't show much of, but we don't have any wind changes. We don't have any. We don't allow wind changes. We don't allow salinity changes. All we do is just try to keep this ocean uniformly. You get basically the exact same patterns out at high latitudes as you do in a couple of simulations. So what it means is that the winds are playing a role, but they seem to be secondary to the ocean circulation. When it's moving heat around in the ocean is kind of the first order thing that sets the pattern of surface temperature change.
Steve Schwartz from Brookhaven National Lab visiting.
Hi. Yeah, I like the presentation, and I kind of like the experiments that you just described, where you can go in there and change one thing and hold other things constant. Doing that with Aquaplanet, I think it's a good way to learn things about the climate system. My question is sort of along the lines of Marat's, having to do with the difference between the step function and say, a ramp forcing. You can think in some sense of a step function as a Green's function kernel for a ramp forcing. And so what we're having in the real world is a superposition of times. So you've got the effect of the forcing that took place in an earlier time, the effect that takes place at a later time, all superimposed. So my question is really, what inferences can you draw about what's happening to the real climate from the step function experiments?
That's a good question. Could you all hear the question in the back, or should I?
I think it's a good idea to repeat.
Repeat? Okay. The question is, what can you learn about the real climate from these kind of idealized step function experiments where you're not you don't have any time history of slow forcing. All you're doing is just hammering it at a given point and looking at the response, which is going to give you a different pattern of warming, for instance, than the observed. I think is roughly the question. So I think the way I present this is really to use the step function to separate all these timescales. The fact that the land warmed very quickly, the low latitude oceans qualitatively warm next, and then the high latitude oceans continue to warm for hundreds and thousands of years at the surface. And so I think what that means for the present day, where you have a slow ramping of forcing, where you don't have this abrupt thing, is that you have, in the slow ramp case, you basically are blending the land and the low latitude oceans timescales together, right? Because we have the CO2 we emitted yesterday, and we also have the CO2 we emitted a decade ago. And so those two timescales are kind of being merged. The thing we don't have yet is any polar amplification in the very long-term sense. It turns out the Arctic always has amplification at all timescales, but the Southern Ocean takes a very long time to start warming and then continues warming for a long period of time. And that's consistent with the observations, where we basically haven't activated the feedbacks in the Southern Ocean yet because we haven't warmed there, but we can be sure we will at some point. But I think when you look at these 1% per year ramp scenarios, what you see is instead of the very clear separations, you see a continuous convolution of those three responses, but it's a blend of low latitude and land together, and then slowly becomes high latitude much later. And so you still see curvature, it's just a slightly different shape to it. Does that answer the question?
Yeah.
Martin?
In the chemistry climate community, there's been an effort to sort of develop metrics that can be applied to the various models to see how they're doing. To what extent can this formalism be used to develop metrics for the climate models to assess their relative realism?
Can we validate it?
Like, you understand the question. I mean, like an abrupt change in some.
No, I mean, he's looking at the spatial feedbacks, and I'm not sure to what extent you could assess in the models as to how the various models might be doing on these spatial.
So I think this work contributes to the discussion because it means that there's a separation between the feedbacks and, say, ocean heat uptake. You can think of these as kind of separable things that you can then go after, because previously we just saw curvature in these models and didn't know why. Now it says that we have a feedback way of looking at it, and we have a forcing from the ocean way of activating those feedbacks. So the feedback structure, I think the best approach is to try to estimate those patterns of feedbacks that are coming from something like Andy Dessler's work, looking at patterns of feedbacks from satellites. The problem is it's short time scales with lots of natural variability, so we don't know how robust those are, if they could change over time. But I think that's the way to go, which is just accumulate more and more decades of the way surface temperature relates to top of atmosphere radiation to try to back up those. That's one approach. The other thing is that most of the pattern of feedback differences across models is due to the clouds. So work on better understanding cloud properties and the way clouds interact with the climate system would help to understand those intermodal differences. I'm not a cloud person, so I'm not sure the way to test those against observations, but that would be one avenue forward. And then the other thing is just understanding the patterns of temperature change, because those, I'm arguing, are kind of independent of the feedbacks themselves. They're much more an ocean story, where different ocean models will give you different patterns of temperature change. And so you can look at which models are simulating the mean state circulations best, and I think those are going to be the models which affect temperature and heat in the ocean in the most realistic ways. And so that would be a way to validate that. But, it's a pretty tough question.
So Kamazima has a question.
So with all this, you left out one important thing. Maybe it was included, I didn't quite notice. Where does the aerosol, because it's always a big issue, what role aerosols play in climate change. When you do this, where does it fit?
Yeah, so I haven't talked about aerosols at all here. I think there would be a natural place to think about it in this context, in the sense that the aerosol forcing itself has a very strong spatial structure. So it doesn't look like this global kind of uniform forcing of CO2, which isn't quite uniform, but it's kind of close. But the aerosols really affect certain regions more than others, and so what this means is that you're going to be affecting the feedbacks in those regions through surface temperature changes. In certain regions versus others. So this could be another way to get a handle on this efficacy of forcing issue, where a global mean 1 watt per meter squared aerosol forcing has a different temperature response than the global mean 1 watt per meter squared CO2 forcing. So I think aerosols could come in through the spatial structure argument, but beyond that, I don't know. I leave it out because the aerosols are large uncertainty. I'm just trying to think about mechanisms here. Does that answer the question?
Yeah, I think so. So Steve, do you have anything to comment?
Yeah, stimulated by Marv's observation in some sense as to what we can learn about the real climate from measurements and metrics. And we had a proposal, unfortunately shot down, which I still think is a great proposal, but it's a one-time only. It was to put really well-calibrated flux radiometers on the Iridium network of 66 polar orbiting satellites so that you would get the picture of radiation from spatially in great detail, which we just don't have now. And I think that the sort of the framework you're dealing with would be a wonderful way to try to interpret the measurements that we would have from that network if we had it.
Well, I won't reject that proposal next time.
Also, Kyle Armour will be will be available to meet with graduate students in the October room between 2 p.m. and 2:45 p.m. So I encourage everyone to visit there and talk to him more about this very interesting work. So let us thank